Hi everyone, I'm Marco Faroni. I'm a researcher of the Institute STIMA of the National Research Council of Italy, and the topic of this work is real-time trajectory scaling for robot manipulators, which fits in the context of online motion planning. As you see in the video, when the nominal trajectory of the robot exceeds its limits, path following errors may arise, and this may jeopardize the quality of the process or even the safety of the movement. Real-time trajectory scaling can be used to modify the robot trajectory at runtime, and this is useful, for example, in technological applications like gluing or laser cutting, but also in more general scenarios where it is necessary to reduce the planning latency. From a theoretical point of view, we should solve an optimal control problem at each time instant, and the first term of the cost function is the path following error, while the second term is the tracking error with respect to desired time and low. Note that in this problem our control variables are the velocity profile along the path, that is v, and possibly the joint variables q and its time derivatives. Solving this problem at each time instant is not a viable solution because of the high computational load, and therefore many methods have been proposed in the literature, and they basically differ in how they approximate this problem. In this paper, we made a comparative summary of the works proposed in recent years, and the main classification is between local methods and look-ahead methods. Roughly speaking, local methods consider the optimal control problem only at the current time instant, while on the contrary, look-ahead methods consider a finite predictive window, and it is therefore straightforward to apply, for example, model predictive control, as proposed by some of the methods. One difference between the methods is the nature of the constraints they can include in the optimization. For example, some methods can only include speed limits, while others can consider also limits on the jerk or on the torque derivative, for example. Another difference is between local and look-ahead methods, as I've already mentioned, and also the fact that some methods do not require optimization tools is of interest, especially in case of commercial hardware with low computational power. And of course, we consider computational load, which should allow for implementations with high frequency. And finally, we analyze the possibility of handling Cartesian trajectories, and in particular to exploit kinematic redundancy during the execution. Let's see some example now. In this case, we perform the same trajectory with and without bounds on the torque derivatives. And the torque derivative bounds have been introduced thanks to this method we published recently. And look at the bottle on the table, for example. It is interesting how we can reduce vibrations and bumps by limiting the torque derivatives, and notice that it is done online in real time with a frequency of 500 Hz. The second example shows how we can achieve small path errors despite the nominal execution time, which is too short for the robot, but the trajectory scaling algorithm slows down the trajectory online and the path is followed correctly. Finally, this is an example on a different robot with a Cartesian trajectory. And here the interesting fact is that we implemented the method on a commercial hardware with very poor computational power, but still the results are quite impressive. So concluding, online trajectory scaling methods can enhance path following by modifying the trajectory online, and they are useful especially when trajectory is generated online or when the environment is dynamic, or when the computational power of the hardware is very poor. And that's it. Thank you, and feel free to email me.